good morning, good afternoon, good evening. Whatever time it is, I do hope that you're having a good time. I'm Andrew Komazensky, and I am an instructor at Hokkaido University of Education, Osaka. This is part of a series of flips on critical thinking. If you're in the class, this would be the 7th flip. If you're watching online, this might be your 8th flip. So, I want to go ahead and get started. So what I want to do today is to talk more about using truth tables to prove the validity of arguments. So first, let's review. So a valid argument is one that follows the rules. And what that means is that if the premises are true, the conclusion will be true. So we call this particular attribute truth preserving. So this is a very important concept. So we call arguments where if the premises are true, the conclusion is true, truth preserving. These arguments use a very small number of operators, and they follow the 3 laws of logic. Those 3 laws are the law of non-contradiction. It is the case that A and not A cannot both be true. So we can't have something where it both is the case and is not the case at the same time. Second, there's the law of the excluded middle, that of A and not A, only one of the 2 can actually be the case. And finally, there's the law of identity, which is that something is always the same as itself. So we learned several different argument forms. So the first of these is modus ponens. So modus ponens is if P then Q, P therefore Q. So be very careful to remember which thing is on the left and which thing is on the right, because it doesn't work if this is reversed. So it doesn't work if the next premise is Q. So if we have P then Q, Q therefore P, that is not a functioning deductive argument. So we also have modus tollens. So modus tollens, if P then Q, not Q therefore not P. Disjunctive syllogism, A or B, not A therefore B. Again, be very careful. A or B, A means nothing. So we need to have a negation. The second one must have the word not in order for it to be disjunctive syllogism. Hypothetical syllogism. If P then Q, if Q then R. Therefore, if P then R. Again, make sure that we have P in the start and at the start. And then we have a middle term, and then we have the same R. So please make sure that this is happening in this way, otherwise it doesn't work. Finally, we have dilemma. So dilemma A or B, if A then C, if B then D, therefore A or D. Or A or B, if A then C, if B then C, therefore C. And we have several standard operators. Negation. Negation just means not. So we have P, its negative is not P, vice versa. Conjunction. A conjunction is true only when both parts are true. In every other case, it's going to be false. A conditional. A conditional is true except when the left-hand part is true and the right-hand part is false. So I know I talked about this in class, for those of you who are taking it. And this is maybe the hardest point to understand about this logic. Why do we do this? The simple answer is that we have to choose based on one thing and one thing alone, which is that we have to make our situation such that A or not A. So this is the law of the excluded middle. We have to pick. And in our case, what we do is we pick to make it the case that this is true, both when it's true that it's obvious, so if P then Q, if both of them are true, that's true. So we saw P, we also saw Q. But we also pick to make it true in every case where P doesn't happen. So if it is raining, then if it's not raining, we will say that this conditional is true. Finally, disjunction. A disjunction is true if either half of the disjunction is true. Okay, so I want to show us how to do this with disjunctive syllogism. So let's look at one. Either you will eat at Mossburger or you will eat at McDonald's. You will not eat at Mossburger, therefore you will eat at McDonald's. This would be my choice. Yours is probably different. So how do we do this using a truth table? So what we will need is a truth table that looks like this. So we're going to need 4 different rows that we can use. Why? Well, that's easy to see. Because we have P, which can be either true or false, and we have Q, which can be either true or false. So to look at every possibility, we're going to write that P is true and Q is true, P is true, Q is false, P is false, Q is true, and P is false and Q is false. So we're going to look at every possible situation for those two. Now, for or is true if either side is true or if both sides are true. So, this is true. True, true is true. True and false is true. False and true is true. False and false is false. So not P. True whenever P is false. So we're going to get false, false, true, true. Finally Q, we can just copy it over. So that's going to give us true, false, true, and false. Our first question is, where is it the case that both premises are true? And the answer is here. Both of our premises are true only on this row. So it's not the case here. We have one true premise, one false premise. One true premise, one false premise. One false premise, one true premise. So now, we need to remember that definition of validity. So an argument is valid if it is the case that when all of the premises are true, the conclusion must be true. So if both premises are true, our conclusion here is true, and we have shown that this is a valid argument. Okay, so that's disjunctive syllogism. So let's move on. So I'll let you see kind of a prettier typed version of that. And we can hold the screen this way for a little bit. Okay, now I want to show you the same thing for a hypothetical syllogism. So we're going to need a bigger truth table. But first let's look at our hypothetical syllogism. So if I sleep in class, I will get a low participation grade. If my participation grade is low, I cannot pass. Therefore, if I sleep in class, I cannot pass. Another one, if Asapi is alive, Asapi eats Brahmin. If Asapi eats Brahmin, our taxes will go up. Therefore, if Asapi is alive, our taxes will go up. Asapi is the yurukara for Asahikawa City. So let's see if we can show whether this is valid or not. So now we have three variables. So let's go ahead and make a chart. So now we need 8 rows because now we have 2 times 2 times 2 because we have P could be true or false, we have Q could be true or false, and we have R could be true or false. That gives us 3 variables. That means we need 8. So I'm going to go ahead and write these out for you. So we're going to go true, 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 false, 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 false. Then we're going to go true, true, false, false, true, true, false, false. Then we go true, false, true, false, true, false, true, false. Now remember, these are our variables. So these are things we're saying are true or not. These are not our premises. So our premises are here and here. Okay, so I'm going to switch that to one where I've got these typed out a little bit cleaner. Should be exactly the same. Okay, now let's look at our premises. So, P implies Q is true when P is true and Q is true, or anytime P is false. So let's go ahead and fill those out. So P is true and Q is true. It's going to be true. P is true, Q is true. It's going to be true. When P is true and Q is false, it's going to be false. So we're going to put that in. So it's going to be true, false, true, 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 like that. Alright, same thing with Q and R. So this is going to be false whenever we have this arrangement. So this is going to be like this. So we're going to get true, false, true, 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 false, true, true. Okay, so this one's interesting because now we have a lot more places where both premises are true. I'm going to highlight all of them for you. Alright, so in this case, both premises are true, both premises are true, both premises are true, and both premises are true. So we have here 4 rows where both premises are true and 4 rows where both premises are false. Let's add in our conclusion. Let's do it in a different color. Okay, so P implies R is going to be true whenever P is true and R is true. P implies R is going to be false when P is true and R is false. So P is true, R is true, it's going to be fine. So we're going to have this little pattern here. Then the last 4 are going to all be true, because whenever P is false, it's true. Okay, so let's look. Let's see if we have a valid argument. So both true premises, true conclusion. Just put a check there. We can ignore all of these, they don't matter. Both true premises and a true conclusion, ignore. True premises, true conclusion, true premises, true conclusion. Again, we can ignore all of these because in all of these cases, one of the premises is false. If a premise is false, we don't need to pay attention to it. So here we have it kind of pretty printed, same results that I was talking about. Finally, I'm going to go a little bit further. I'm going to show you how to do this for a dilemma. So, either you will eat Italian food or Chinese food. If you eat Italian food, you'll go to Caesarea. If you eat Chinese food, you will go to Osho. Therefore, you will go to Caesarea or Osho. So this one has 4 variables. So if there are 4 variables, how many rows would I need? Alright, the answer is 16. So I would need 2 for I. Then when I add C, I'm at 4. Then when I add S, I'm at 8. And then when I add O, I'm at 16. I don't really want to write out 16 right now. So what I'm going to do is show you the dilemma where both of the conclusions are the same. So, in other words, you need 2 to the number of variables. So this could be helpful for some of you, to know how many rows for a complete truth table method. So, here's the dilemma I'm going to give you. Either you will marry Tetsuya or you will marry Shin. If you marry Shin, you will become a mother. If you marry Tetsuya, you will become a mother. Therefore, you will become a mother. So let's look at this one together. So I've already done this table. This is the same on the left as the other one that we looked at. Again, we've got 4 trues, 4 falses, then 2, 2, 2, 2, then flipping back and forth, one after another. Okay, A or B is true whenever either A or B is true. So let's go ahead and fill these in. So the first 2 are going to be true. Third one's going to be true. Fourth one's going to be true. Fifth one's going to be true. Sixth one's going to be true. Seventh, false. Eighth is false. Alright, A implies C. This is true except we have this connection. So we have true. We have false. We have true. We have false. And the rest of them are true. B implies C. So that's going to be false when we have that same connection. So this is going to give us true, false, true, 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 false, true, true. Okay, so again, I'm going to highlight all of the rows where both premises are valid, because validity only matters if both premises are true. If the premises are not true, it has no connection to validity, because the definition of validity is that an argument is valid if, when all of the premises are true, the conclusion is also true. So, all true premises there, all true premises there, all true premises there. So I don't need to pay attention to any of the other rows, because in all of the other rows, at least one premise is false. Our conclusion, C or C. True whenever C is true. So true, false, true, false, true, false, true, false. So in all 3 cases where the premises are true, the conclusion is also true. So true, true, true. So we have now shown that a dilemma is valid. If we did this with 4 variables, it would just look a little messier, same results. So here it is in kind of pretty printed form. I will leave it up for a couple of seconds. You can pause your screen if you'd like to look at it longer. So, the key to understanding validity is to follow the rules. So there's only a very small set of rules, and when we merge these together, then every claim must either be true or false due to the law of the excluded middle. Every formula must also be true or false due to the law of the excluded middle. So things that don't make sense don't work in this world. It's a very simple world. Very nice in that respect. So let's think a little bit more about this. So let me show you another one. So if Dr. K is an American, then Dr. K likes pizza. If Dr. K likes pizza, then Dr. K will eat at Mia Boca. Thus, Dr. K likes Mia Boca. So we've seen this before. And what this is the same thing as a hypothetical syllogism. So we've already seen this. So I want to talk with you a little bit more about how we can think about this. So far what I've told you is that when all of the premises are true, the conclusion must be true. So let's look at another test of validity. In this case, I want to show you something and ask you if you can figure out whether or not it's valid. I've already made the truth table, so we'll just work through the steps after that. So I will read the argument to you. If Dr. K is an American, then Dr. K likes pizza. If Dr. K likes pizza, Dr. K will eat at Mia Boca. Mia Boca is a restaurant that does Hokkaido and Italian food together. If you ever come to Asekawa, you should give it a shot. Also in Sapporo. But let's see if this is a valid argument. The first thing we need to do is we need to highlight all of the rows where both premises are true. So both premises are true here, both premises are true here, and both premises are true here and here. Alright. Remember, the definition of validity is that an argument is valid if it is the case that it cannot have all true premises and a false conclusion. This argument is invalid. There's two rows that show why. Here and here. So what does that mean? Does it mean that I don't like Mia Boca? No, I do like Mia Boca. What it means is that based on these two premises, you do not know enough to conclude that I like Mia Boca. Now, if you added as a premise that I am an American, then this argument would be valid. Because if you added that as a premise, then it would cross these two out. So if you add a new premise that says I'm an American, so if we add up here, if we added a 0 that says Dr. K is an American, then we could cross out these bottom two rows and our argument would be valid. But right now, it would be possible to have the same argument and have it not be valid. So if we switched, instead of having it be Dr. K, if we said someone else, if we said that Prime Minister Abe, if Prime Minister Abe is an American, then Prime Minister Abe likes pizza. If Prime Minister Abe likes pizza, then Prime Minister Abe will eat at Mia Boca. But in that case, Prime Minister Abe is not American, so then we can know these things. So unless we add this premise, the argument is invalid. So I'm just going to show you a little bit more about that. So same idea, same thing going on here. Alright. So we could do truth tables for any of a number of arguments. So I'll give you a little bit of time to just look at the screen, and I will give you some of the results for this. P, therefore Q. Therefore not P or Q. This is valid. A implies B, ergo B implies A. Invalid. A and B, thus A or B. Valid. A implies B, B implies C, therefore not A or C. This is valid. Okay. Not P or Q, not P and Q, therefore X. This is invalid. So I can show you any of these using a truth table. So for instance, let A and B, thus A or B. Using a truth table, we could see this, because A and B is true only at the top of that truth table. So A and B is true. On the same row, A or B is true. So anywhere that A and B is true, A or B is also true. So there's actually an easier way to do these problems. So I want to talk a little bit about that. So let me just switch things up a little bit. Means if the premises are true, the conclusion must be true. So what we've done so far is we have looked at every possible way to get to the premises to be true, and every possible way that everything can be, whether it makes the premises true or false. And then we've seen, in the end, when there are all true premises, is there a true conclusion? Or to put it another way, until this point, we've been heading this way. So what I want to mention to you is there's a second way to do this. And the second way to do this involves going in the opposite direction. So this is called truth tables. And this is called the short circuit method. So the short circuit method works backwards. Here's how the short circuit method works. So let's say that we're looking at modus ponens, which we've already done a couple of times. So modus ponens is this. So we have P implies Q, P therefore Q. So this is modus ponens. So let's say that we wanted to prove this using the short circuit method. So we're going to do the same basic thing. So we're going to start by putting a truth table chart up. Well, we're going to do something different here. So let's just go ahead and put our rows in. But here's what we're going to do. So before we started from the left and moved right, we're going to start from the right and move left. And here's what we're going to do. I'm going to write one big giant F here. So we want to prove that this is valid. So we're going to see if we make this conclusion false, can we make both premises true? If we can, the argument is invalid. If we cannot, the argument is valid. So what we just did makes it so that Q has to be false everywhere. Alright, if Q is false, then this premise will be true in every case except where P is true and Q is false. So now, because of this, we know that to make this premise true, we have to make P false. But if we do that, this premise becomes false, because P would then be false. We can do this backwards too. So let's say we make this P true. So if P is true and Q is false, then this is false. So what we've shown is that we cannot make this argument have a false conclusion and true premises. Let's look at something that we know is invalid. So I'm going to look at affirming the consequent. So affirming the consequent looks like this. Affirming the consequent is A implies B, B, therefore A. So we're going to do the same thing. So we have A, B, A implies B, B, and then A. Alright, so let's split these parts up. Let's not bother going to the edge. So we're going to set that conclusion to a big false. So now we know that A, to show if it is able to have all true premises and a false conclusion, A must be false. Got that. that. Alright, how does this help us? So B is one of our premises. So let's start by saying what happens if we make B true. If we make B true, that means that B is true. A implies B. A is false, B is true, that's true. So, we have shown this is invalid because we have shown it can have both true premises and a false conclusion. So, this is how this method works. So we go backwards. So we didn't have to write 3/4 of this table because we started with our conclusion and set it false. The only difficulty here is you have to think a lot harder to solve problems this way. But if you can do it well, this is much faster as a method for solving these sorts of problems. So far today we've looked at the short circuit method and the standard method for using truth tables to resolve problems. So again, the goal of a truth table is to test the validity of a deductive argument. This works from saying an argument is invalid when all of the premises are true and the conclusion is false. This means we do not need to fill out the entire truth table, but only those rows that mean the conditions to show validity or invalidity. So that's the basic idea that we're looking at here, is that we are short-circuiting by doing this. If these are true, the conclusion must be true. So here, what we did is we start by making the conclusion false. We then see if we can make the premises true. And if we can, it's invalid. So I'm going to show you one more difficult example, and that's going to be it for today. So we have A or B and C, not B and C, thus A. First thing we're going to do is we're going to set A to false. So once we've done that, we have our variables over here. We can go ahead and set that one. Alright, but if we've done that, now we need to figure out what we have to do to make our premises true. So we're going to have to make a little bit bigger of a truth table. So let's look at all of the possibilities. So we already know this is false. So then we've got B either true or false, C true or false. If we do that, B and C is only true when both of those are true. And then A is false. Alright, but then not B and C is false. So what we've done to ourselves here is this is not a true premise. Alright, if C is false, not a true premise, not a true premise, not a true premise. So what we've done is we have shown that there is no way to give this argument all true premises and a false conclusion. Well, thank you for listening.